Next up, we're just gonna do an example of trying to find one of those potential functions f. So if we're given some capital F equal to x, y, z, we want to find little f, a potential function, such that the vector field capital F is the gradient of that little function f. So from the first step of our solution process, we know that we need to solve the equation where the f that we were given, x, y, z, is equal to a gradient vector, df dx, df dy, and df dz. The challenge here being that we don't know what that little f is. So we're going to take this one thing that we want to be true and turn it into three equations. We know that df dx has to be equal to x. We know that df dy has to be equal to y. And we know that df dz has to be equal to z. And so right now, if you wanted to, you could try to think about those are the rules for what you need the partial derivatives of little f to be. And you could sort of guess and check and try to figure out what little f is just based on that information. The process that we learned in steps is kind of a process that we can always follow to try and get the answer that avoids guessing and checking. So we rearrange our three equations right here to give us three solutions for f that we get by integration. So integrating the first equation tells us that if we integrate, a dx was what we had in our step-by-step process. But if we integrated x right here, then we would get f on the left side, and we would take that integral with respect to x, and it would give us that k1 that we don't necessarily know and can't recover by only taking the integral of x with respect to x. If we look at the second equation, if we integrated y right there, that integral being with respect to y, that would give us f if we added on some unknown constant k that could depend on x and z. Or from the third equation, if we integrated z with respect to z and remembered to account for the unknown constant that depends on x and y, that would also give us little f. So the next step of the process is we evaluate these integrals because we might not know all those k's, but we do know how to take integrals with respect to one variable. So the integral of x with respect to x from that first equation is just 1/2 x squared. The integral of y with respect to y from that second equation is 1/2 y squared. And the integral of z with respect to z from that third equation is 1/2 z squared. So they're all very similar because we had x, y, z in the x, y, z coordinates. Here's where it usually gets tricky. We would have those steps 4, 5, and 6 where we go through and we cross out things. So we would say, okay, x dx gets to stay however it is. We got 1/2 x squared, that's fine. And then we would check this term and cross out anything that's a repeat from the first. But 1/2 y squared is different from 1/2 x squared, so we don't have to do anything here. Then we would go on to the third thing that we solved for, and we would check back to the second and check back to the first, and we would cross out anything that matches those. But 1/2 z squared is different from 1/2 x squared, and it's different from 1/2 y squared, so that can also stay where it is. So up to this point, we've done all those steps. And I'll go ahead and denote that kind of off to the side here, we did 4 through 6, and just getting those integrals was step 3. Here was step 1, and here was step 2. Actually, I think step 2 started here. Sorry. And then now, we would take that step of saying f is going to be the sum of everything we got from our integrals without those repeating terms. So we would take first that 1/2 x squared that we got from step 4. We would add that 1/2 y squared from 5, and then we would add that 1/2 z squared from the 6th step. And at this point, we've got the answer to that question. Little f equal to 1/2 x squared plus 1/2 y squared plus 1/2 z squared is the potential function f that generates the vector field we were given. So I want to note a few things about this solution because this is a really odd new process for us. Now that we know that little f is equal to 1/2 x squared plus 1/2 y squared plus 1/2 z squared, we could solve for what was this k1 of yz. So integral of x dx was 1/2 x squared, and then we had this k1 of yz that we didn't know, and that's what stopped us from finding little f. But now we know that the extra part of little f that we were missing was 1/2 y squared plus 1/2 z squared. So k1 of yz was 1/2 y squared plus 1/2 z squared. This placeholder right here for some unknown constant that comes out of our integral x dx we found by solving these second two parts. And sort of you might have already noticed, but this 1/2 y squared plus 1/2 z squared is the exact same as the part of f that's going to disappear or drop out from the x component of the gradient. Oops. When we calculate it for little f. So if we started from here, little f, not knowing where we came from, we do have the tools to calculate the gradient vector. I would take the derivative with respect to x. That's just going to be 2 times 1/2 times x squared. Sorry, 2 times 1/2 times x would just give me x. And then 1/2 y squared, the derivative with respect to x is 0. And 1/2 z squared, the derivative with respect to x is 0. Derivatives with respect to y give me 0 plus y plus 0. And derivatives with respect to z give me again 0 plus 0, then plus z. And so this 1/2 x squared in little f leads to the x that we see in the gradient vector. But these other two terms, 1/2 y squared plus 1/2 z squared, they don't show up in the x component of the gradient vector. And they also don't show up when we integrate with respect to x on the gradient vector, integral of x with respect to x. So it's just important to remember when we're working through this process that, for example, y and z are constant in relation to derivatives or integrals that we take in x. So you're probably already familiar with that in practice. You've done lots of partial derivatives and integrals with respect to one variable. And it just comes out in this weird way where in this type of problem, we need to compute integrals for all variables to make sure that there are no missing terms. In your little f. Because if you integrated with respect to only one variable, like if we integrated x dx and stopped there, we would never pick up those y and z constants that don't show up in the gradient derivative with respect to x. And then just to be clear, this sort of like discussion and checking that I did is not necessary to solve the problem. We were good when we stopped here. I only did that to highlight why we have this funky notation reminding us that there are unknown constants that depend on variables in these integrals, and also why we have to do integrals with respect to all variables. You can't just stop after one or two.